So complex analysis, practice final exam part 4, number 10, consider the function f of z equals square root of z squared minus 1. Part A, identify the branch points. Part B, construct a branch of f on a complex plane with -1 and 1 removed. Part C, determine the behavior of your, so that was part B. Part C, determine the behavior of your chosen branch as z approaches infinity. And part D, explain why f cannot be defined as a single-valued holomorphic function on complex plane with -1 and 1 removed. So this is analytic continuation and monodromy. So the branch points are going to be just z equals 1 and z equals -1. Sorry about that. And to define a branch on the complex plane with -1 and 1 removed, we choose f of z equals this exponential, that 1/2 the principal log z squared minus 1. Specific branch there where that principal log z squared minus 1 is chosen so that f of z is asymptotic to z as z approaches infinity. So the branch is characterized by the square root of z squared minus 1 is asymptotic to z as z approaches infinity. For large z, square root of z squared minus 1, that equals z times the square root of 1 minus 1 over z squared. And that's asymptotic to z times the quantity 1 minus 1 over 2z squared. And that equals z minus 1 over 2z. So f of z equals the following here. And the function cannot be single-valued and holomorphic on the following because a loop encircling one branch point changes the sign of the square root. Analytic continuation around such a loop sends the following. This maps onto this. So no, sorry about that, inserting here. So no globally single-valued branch exists on the twice punctured plane. Okay, so that's just an overview of number 10. And now moving along into number 11. So number 11, we let p of z equal that product from n equals 1 to infinity of that 1 plus z squared over n squared. So part A, show that the product converges uniformly on compact subsets of that complex plane. Part B, determine the zeros of p, including multiplicities. Part C, compare p of z with hyperbolic sine of pi z and conjecture a closed form. So infinite products here, so p of z equal the following. And for compact, absolute value of z is less than or equal to capital R. Absolute value of z squared over n squared is less than or equal to capital R squared over n squared. And since this sum n equals 1 to infinity, r squared over n squared converges, the infinite product converges uniformly on compact subsets by Weierstrass product convergence criterion. Therefore, P defines an entire function. The zeros are going to occur when 1 plus z squared over n squared is 0. So z squared equals -n squared, and z is going to equal plus or minus in. Each zero is simple because each factor has simple zeros, and no two different factors vanish at the same point. So the zeros are z equals plus or minus in, where n equals 1, 2, 3, on and on and on, all simple. And the classical product formula is hyperbolic sine of pi z equals pi z, and the product from n equals 1 to infinity, 1 plus z squared over n squared. So p of z equals hyperbolic sine of pi z over pi z. And at z equals 0, the right side is interpreted by removable continuation and equals 1. Matching p of 0 is equal to 1 there. Okay, so that's part 4, and thank you very much, and have a great day.